Okay, hi, my name is Paul Eastham and I'm Associate Professor in the School of Physics, and I run a group of theoretical and computational researchers looking at quantum dynamics, quantum physics, with a particular emphasis on the behaviour of light and matter and what happens when you couple light and matter together and what happens when you kind of control the way they behave. So kind of what you can do with this, whether you can make new physics and use it to understand new physics, or whether you can make new devices and use them for something interesting. And we do this using a variety of techniques. Really, it comes down to kind of what suits the individual student. These range from pencil and paper calculations based on simplified models, often using techniques of quantum field theory, right through to computer simulations. And we also work quite closely with experimentalists where we can. It's not always easy, because one of the exciting things I think about this area of work is you can do theory and kind of try and address fundamental and cool questions, but you can do it and really be hooked in to some experiment that someone's doing in the lab and see perhaps the ideas you developed in theory come to life in an experiment. So I'm looking for students to join the group and perhaps through the IRC funding stream. And one of the areas I'm particularly interested in looking for a student to work on is an area we work on already, which is open quantum systems theory, and developing that into a tool for inverse design of quantum sensors. So what's an open quantum system? Well, we're talking here about some nanoscale system like a single atom or an impurity inside a semiconductor, a quantum dot, or a superconducting circuit or something like that. There's a quantum system with maybe a few discrete energy levels. That's the thing we call a system. And there's a lot of interest now in using these controlled quantum systems, these small things, often qubits, to build devices and to study their properties and use them to explore physics. But one of these things about these devices and these structures is this small quantum system is never really isolated. So if you have, for example, an atom, it's not just the atom, it's talking, say, to the electromagnetic field, and that leads to the process of spontaneous emission, where the energy goes out of the atom into the field. More generally, all these things, like superconducting qubits and quantum dots, you have a small quantum system, but there's all sorts of complex surroundings to this. Maybe it's inside a solid, and so there's all the environment of this device that it's sitting in. And this can have very profound effects because it's actually the interaction between this quantum system and its environment that destroys many of the weird behaviors of quantum mechanics, things like entanglement and superposition. So the Schrödinger cat being both alive and dead, well, if the Schrödinger cat interacts with the bigger environment, then it doesn't stay both alive and dead for very long. So one of the challenges is that studying open quantum systems is really a problem in quantum mechanics that's very hard to solve, and until recently there's not been any general way of solving what happens if you have a small quantum system interacting with a wider environment. But in the group we've been working with colleagues in St Andrews, and we think we've got techniques that essentially allow you to simulate this problem exactly in full generality in a realistic setting, and we combine those with analytical studies to kind of get insight into what's going on. So that's the kind of background to the project I'm thinking about. The actual project is really to use this to build a tool, an inverse design tool for quantum sensors. So what's a quantum sensor? Well, a good example is the proposal by my colleague Ortwin Hess, Professor Ortwin Hess, to use a little metallic nanosphere to detect molecules, maybe proteins. So what you do to do that is you put a quantum emitter, a little nanoscale quantum system on your protein, you tag it, and then you've got this metallic nanosphere which controls the electromagnetic field and produces very strong resonances in the electromagnetic field with a very high electric field. And if the quantum emitter is at the position of this resonance, that leads to a change in the spectrum of the emission from the electromagnetic field, and basically you get, instead of one resonant peak, you get two. So what I've just described is a quantum sensor and a quantum sensing protocol. The protocol is, I take this thing, I drive it to excite it, I probably shine a laser on it, and I look at the emission spectrum and see what comes off, and that tells me whether the molecule I want to detect is there or not. Now, there are many examples of quantum sensing protocols in many different systems, but they've all really been derived from our understanding of things like nuclear magnetic resonance and some simple cases of the behavior of open quantum systems. So that probably means we're missing all sorts of things we could do and all sorts of accurate, fast approaches to quantum sensing that kind of exploit the weird and wonderful world of quantum mechanics. So the proposal, the area I would be keen to develop an IRC proposal with a student in, is to look at whether we could do inverse design of quantum sensing protocols. And what that means is, instead of just kind of guessing a protocol that will work based on our understanding of physics, we set up a simulation that can explore all sorts of different protocols very, very fast, and can navigate through this huge space of possible protocols to find the ones that perform well, to perform better, and hopefully outperform any existing classical protocols. And kind of the advantage of this is that it can discover things you would never have thought of based on your kind of understanding of physics, because that's probably incomplete. Now, to do that's very hard. You need a fast way of simulating the system, and you've got to do that many, many times because you've got to explore all these possibilities of a different device. We've developed general ways to do that kind of problem with our colleagues in St Andrews, and the idea of this would be to take that basic framework and develop it and apply it particular to the development of quantum sensing protocols. So this would involve both computational work, but also understanding and building your understanding of the kind of fundamental physics and things like how you quantify the amount of information in a measurement and things like this. So if that's something you might be interested in, please do get in touch